Leo, can you message Roman and say do a tech check over lunch? Roman, with the virtual talk, we want to do a tech check over lunch because share screens.
Is this okay? I'll just. That's on. But does that mean I can't walk around? Is this okay?
You should be able to. I think they can unmute it.
All right. How do I advance? Is it this? All right.
You ready?
Ready when you are.
All right, let's go ahead and get started. You enjoyed your first coffee break. Now you have some more caffeine. Let's go ahead and get started with session 1, part 2. And to lead off, we have my colleague Hannah Diamond-Lowe to share us an update about the Rocky Worlds DDT. Take it away.
All right, thank you. Can you hear me? Is this on? Yes, okay. Thank you very much to the organizers for putting together this workshop and for allowing me to contribute what will essentially be a 10-minute infomercial on the Rocky Worlds DDT program. So to give you a bit of an overview of where this program came from, this was a direct recommendation from the report of the Working Group on Strategic Exoplanet Initiatives with HST and JWST. There was a lot of community input to this report, including town halls, white papers, and a survey that eventually led to a lot of recommendations on this strategy, but in addition, a recommendation for a large director's discretionary time DDT program. The director acted on this recommendation, and then this led to the creation of a core implementation team here at Space Telescope. So these are the folks that are actually making this program happen, who are working on, a lot of them are working on scheduling and processing data, but we also have folks who are working on software, publicly available notebooks, and of course communications to the general public and the astronomical community. We have an external council of researchers who we meet with monthly to get recommendations for anything from target selection to observation strategies to new community initiatives. So they are also putting in a lot of work. They are also sort of your representatives to us who are actually making these observations possible. So what is the science that we hope will be accomplished from this large investment of telescope time? The main question that we were tasked with is, do M-dwarf rocky exoplanets have atmospheres? And the way that we have decided to go about answering this is to frame it in the lens of the cosmic shoreline concept. And does this cosmic shoreline exist for M-dwarf rocky worlds? And so, of course, the sample that we need to answer this question are rocky exoplanets that are transiting nearby M-dwarfs. So here's this cosmic shoreline concept. You've perhaps seen this before, and you may see it again before this workshop is over. So this is essentially high energy radiation received by a planet as a function of that planet's escape velocity. So sort of down here, where you have not so much high energy radiation and a very high escape velocity, as we've sort of heard already, that's a clue that maybe planets down here might be able to hold on to an atmosphere. The opposite would be said for planets in this upper region, where that receive a lot of high energy radiation and have a lower escape velocity. Of course, this concept was developed, and we know that it works only for the solar system. So the solar system rocky planets are on here: Earth, Venus, Mars, and Mercury. Earth and Venus, down here in the atmosphere-likely region, do have atmospheres, so that works out. Mercury does not. Mars dances right on the shoreline with about 6 millibars worth of surface pressure from an atmosphere. But every other point on this figure is not in the solar system, right? These are M-dwarf rocky planets. So we've plotted them in this parameter space, but we do not know if this cosmic shoreline applies. Hence the question, does this cosmic shoreline apply to rocky exoplanets orbiting M-stars? It could be this line could be somewhere else, there could be no cosmic shoreline, right? So that's kind of the objective framing of the DDT. How are we doing it? We're focusing on secondary eclipse observations of these rocky planets. So we assume that these rocky planets orbiting their M-dwarfs are tidally locked and synchronously rotating, meaning they have the same face always facing their host star, similar to the moon always facing the Earth, which means there is a permanent day side and a permanent night side. If there is a lot of flux coming from that day side, you would measure something that looks like this. So in this schematic of normalized flux versus time, before the planet passes behind the star, you're actually measuring flux, you're measuring photons from the star plus planet system. When the planet goes behind its host star, you can actually determine how much of that flux, what fraction of that flux was coming from the planet's day side. If you are missing a lot of flux, and that means that a lot of flux was actually being donated from the planet, this would be an indication that the planet is a bare rock. If you instead have a lower day side flux from that planet, this may arise from an atmosphere around that planet shifting energy incoming from the host star from that day side around to the limbs or even the night side of that planet. And you would actually measure a shallower depth, less flux coming from the planet. And this could be a clue that maybe there is an atmosphere there. We get another trick, another bonus, is if you look at 15 microns, there is a really big and well-measured carbon dioxide feature. So if you have this carbon dioxide absorption happening from carbon dioxide in the atmosphere of the exoplanet, you measure an even smaller depth, and this is helping you to distinguish from the atmospheric case versus the non-atmospheric case. We have the tools to do this with JWST. The MIRI instrument can measure time series very stably in secondary eclipse when the planet passes behind the star. It has this F1500 wide photometric filter that is gathering a lot of light right around this 15 micron carbon dioxide bonus. So JWST is going to be gathering these eclipses. Complementing this, we will also be gathering UV data from the star itself with HST, with Hubble Space Telescope, which will perhaps give us a clue as to why these planets might be bare rocks or not. That Hubble data is going to look a little different. It is spectral. We are going to be observing flux as a function of wavelength of the complete far UV to near UV, and actually out farther even into the blue optical, so we can relate these UV spectra to optical observations. These wavelengths cover the cross-sections of many molecules you may be interested in, but this is going to form a sort of core base data set for the DDT. In addition to the spectral information, we are also going to be able to look for flares coming from these M-dwarfs. This is not from the DDT, it's an example. We don't have this data yet. But every data set that we can will be observed in time tag mode with HST. This means that every photon comes in has a time associated with it. And we will actually have a flare monitoring campaign within the HST observations. So those will be 3 visits of 4 orbits each with the COS G130M grading. That's the far UV grading, and we'll use that to look for flares, like you can see here in the example. Great. Okay, so where are we at? Targets and status. We are not very far along into this DDT. It takes a long time to schedule these observations, but we are at the point where we have the targets selected, so they've been on here the whole time. Maybe you've noticed these gold data points are the Rocky Worlds DDT targets. There are 9 of them. If this does not sound like a lot of targets to you, I really want to stress that these cooler targets, especially as you get into this region of parameter space, produce extremely small signals, tens of ppm, maybe 100 or so. And if you want to actually detect that in a statistically significant way, you need to stack a lot of eclipses together. You need a lot of JWST time. This is why it's a bold director's discretionary program. So these are the list of the 9 targets. These are available at our website, which I'll mention in a second. One target actually already has data that we have in hand, and there are data products that are available to you. The scheduling team here at Space Telescope is working really hard on scheduling these next 4 targets, and then following we will schedule the last 4. Okay. More updates will come throughout the year, but I do want to talk about a couple of community initiatives. Yes. Okay. So I really want to stress that the Rocky Worlds Director's Discretionary Time Program is for you. We are not doing the science. We are providing a big data set that you can use to do your science, you can build on, you can use directly or use complementary programs. There is zero proprietary period for any data that comes in for the DDT, and our goal is to keep you updated and also provide data products in a timely manner. So this is our website. I have stickers with the website on it if you want to affix them to your devices. This will include news and announcements, including this talk, I believe. So anything that is released will be on here. We also have this really nice scheduling and status page where you can get anything for the program information, our APT files, reports that our team puts together. So we really go into the decision-making process for each data set. This is constantly updated, so please check there. We also have a high-level science product page on MAST. So there you can go to actually download not just the raw data is always on MAST, but here you can download data products. So process data, some fits. This is from one of the secondary eclipses of GJ3929b from JWST. And also we have HST measurement of the Lyman alpha line. So the data processed and the models are available to you. And finally, I want to advertise, it's a sort of pre-advertisement, that we will have a Rocky Worlds Data Challenge sometime next year. We are currently in the planning phase, but we have secured funding and a plan. This is going to challenge the community to analyze Rocky Worlds or Rocky Worlds-like data to compare results with the ultimate goal of landing on some best practices for data reduction, as well as publicly available tools. This will culminate in a 3-day workshop at Space Telescope, and this will be announced in March, so please keep an ear out. And I'll sort of end it here, which is basically to drive home this beautiful picture of the Rocky Worlds DDT, which is focusing on secondary eclipses of transiting exoplanets orbiting M-dwarfs. This is a multi-mission initiative from Space Telescope, so it's really combining the capabilities of JWST's mirroring instrument with HST's UV instruments to really make a sort of foundational data set for the community. Thank you.
Awesome, thank you, Hannah. Any questions about the DDT? Shreyas.
Hey, Shreyas, so from the Carnegie Observatories, I'm curious about how well the eccentricities of these systems are known and how they, if that propagates into the scheduling at all.
Yes, that's actually the largest impediment to scheduling. That's why it takes so long. So though these planets are a tidally locked planet does not necessarily need to have zero eccentricity. We think they should be circular, but as you get to cooler planets, they are cooler because they orbit farther from their stars. So our coolest one is LHS 1140b that has an orbital period of about 25 days. Even small eccentricities in that orbit would lead to uncertainties in eclipse time of hours, many, in some cases, tens of hours. We cannot schedule 50-hour visits, or we don't want to. So a lot of work is going into gathering RVs, doing global fits, using actually high-precision transits from JWST. So if, like, say, JWST NearSpec observes a transit, that's a very good constraint on E sine omega that we don't have before. We really want E cosine omega, but that still helps. And so this is kind of the process of gathering all of that, doing these intensive global fits that include RVs, transits, stellar models, to try to constrain that eccentricity. Yeah.
Katie?
Thanks, Hannah. This is Katie Bennett from Johns Hopkins. I'm excited for this. I was wondering how set in stone the number of eclipses per each target are. Like if you get 10 eclipses for 1140b and it seems like you need 11 or 12, is there any
No, that's a great question. And actually we do a lot of work on the front end to set that number. There are numbers released, they are tentative. We have not released the actual true number of eclipses for 8 of the 9 targets, the one that's already scheduled we have. So check back. The reason we do that is we want to also create a data set that is sort of statistically robust. And if you keep changing the number of eclipses you're going to observe as data comes in, you have a huge bias there. And it's very difficult to sort of disentangle and what is the underlying distribution when you're just kind of keep chasing, you don't have a standardized data set. So we can predict, based on previous observations, exposure time calculators, what the uncertainty should be, and then how many of those you need, accounting for that uncertainty to get a statistically significant detection of the eclipse, and then a statistically significant detection of perhaps an atmosphere or not. We actually have this 2-checkpoint strategy, which I encourage everyone to read about on our website and our strategy page. But it tries to account for that while still being efficient with our observations. Yeah.
I think we're unfortunately out of time there, so please follow up with Hannah, maybe at lunch. So let's thank her again.
Oh, you want my mic? No, I don't want to keep it.
All right. Okay, next we have Renata Frelikh, who will tell us about the impact of radiative cooling on driving hydrodynamic outflows. Take it away.
Thank you. Hi, I'm Renata Frelikh from LASP at CU Boulder, and I'm going to present my work on modeling atmospheric escape from planets starting from the hot Jupiter regime all the way down to the terrestrial planets. I make detailed 1D models of these outflows to understand what drives hydrodynamic escape and what can impact the mass loss rates from these planets. I'm also interested in what current observations of hydrogen escape can tell us about the chemical makeup of the planets. For example, can an observation tell us that the planet is a rocky planet surrounded by a hydrogen envelope, or is it, for example, a water world undergoing photodissociation and hydrogen escape? I'm going to start with the hot Jupiters as they are the most readily observable. Before moving on to my current work, more on the terrestrial planet side. I'm first going to talk about the energy-limited approximation, and then I'll tie it into how I analyze the results of my simulations. So here's the basic structure of a planet undergoing hydrodynamic escape. If I consider a spectrum of only one EUV energy to represent the average EUV photon, optical depth 1, so the tau equals 1 circle over here, is the region where most of the photons are deposited. And above tau equals 1 is the thermosphere. That's the region that exists from EUV photons heating the atmosphere to temperatures of order 10 to the 4 Kelvin. Once the atmosphere is heated enough, the pressure drives a wind out. The energy-limited approximation, as Ruth already introduced, is really just a statement of conservation of energy. The flux coming from the star, Fxuv, hits a cross-sectional area of the planet, pi r squared, driving a wind out, gm over r times m dot. And I've highlighted 3 parts of this formula. The first is the efficiency factor, epsilon, that accounts for losses due to ionization, dissociation, and radiative processes such as atomic and molecular cooling. The second is the XUV flux, Fxuv, and I'll show later that actually the highest energies tend to be less efficient at driving the wind because of radiative cooling and secondary ionization. And the third is the deposition radius. Hot Jupiter models show that the deposition radius can be within 10 to 20% of the optical transit radius, but looking ahead for smaller planets, it can make a bigger difference. It's especially interesting because the deposition radius for the smaller planets can change with time as the atmospheric composition changes. So I'm interested in how radiative losses decrease the efficiency of atmospheric escape, and also what energy bends of the spectrum contribute the most to drive the wind. So for that, I wrote a 1D time-dependent code that couples solving the 3 fluid equations that Anna thankfully introduced earlier with a hydrogen and helium chemical network, including ionization. I solve everything self-consistently without assuming any kind of equilibrium. I time evolve my models to steady state, and here are my results for the fiducial planet hot Jupiter HD 209, for which I used a solar EV input spectrum. So Here's the actual composition of the planet with altitude. The left panel is zoomed into the base, and the right panel shows the larger scale outflow. So this molecular hydrogen layer in green is shown here, and it contains the red H3+, which is an important infrared coolant. Going further up, the temperature rises, so the H2 thermally dissociates, creating this atomic hydrogen layer, which is the source of our other very important coolant, Lyman alpha cooling. And finally, that transitions into the larger scale ionized hydrogen outflow. So here's the 4-panel plot of my density, velocity, pressure, and temperature. I just want to highlight for the velocity in panel B that the wind reaches about 8 kilometers per second at the sonic point. And in panel D on the right bottom, the temperature sort of starts out at 10 to the 3 Kelvin at the base, and it quickly gets heated up to 10 to the 4 Kelvin, at which point Lyman alpha cooling can kick in. And thermostats the temperature to 10 to the 4 Kelvin. So it only kicks in when it's hot enough, but it prevents the atmosphere from heating any further. And then finally, the outflow cools the wind as you go further up. I'm going to talk a little bit about the energy deposition and cooling in the atmosphere. So instead of just one optical depth that I've drawn before, you have an energy-dependent optical depth. So photons of different energies are deposited in layers. The highest energy photons are deposited further in, where they're cooled by the H3+, and also ionization has a significant component. Higher up, you have the atomic hydrogen layer that's cooled by the Lyman alpha, so intermediate energy photons are cooled away there. And finally, photons closer to 13.6 eV are deposited in the outflow region, where they drive the wind. So this energy limited expression has this total flux and the XUV, but what we found is that a lot of the incoming heating, especially due to the higher energy photons, is actually going into secondary ionization or H3+, Lyman alpha cooling. So this efficiency is not a constant. It depends on the photon energy and where the energy is deposited in the atmosphere. So here's a plot that Ruth showed a version of before of the energy balance in the atmosphere. Again, the left is zoomed into the base. So the blue line at the top is kind of the total energy deposited from the EUV. The magenta is the energy available to heat the gas after accounting for the primary and secondary ionizations. So this magenta term can either go into the H3+ cooling in red, it can go into the Lyman alpha cooling in purple, it can be advected around, that's the gray term, or sort of, as Mike said, as a last resort, it can go into the PDV work, I guess. So you can see here that like on the left, in the base, a lot of the energy does go into either ionization or into radiative cooling. And this is also where the EUV absorption peaks. So here, I guess I wanted to show this plot because I wanted to show how not energy limited this scaling is as you move the planet around further and closer into the star. It's the mass loss rate as a function of distance for our grid of models. And on the top, I've turned off radiative cooling and conduction, so that orange line shows our model results, and the black dashed line is just the energy limited approximation with that efficiency of about 0.5, just to account for ionization. So without radiation, it follows the scaling well. But when we turn on radiation, the green dashed line is our model result. Here, the black solid line is the energy limited approximation with an efficiency of about 0.1, where we've tried to account for ionization and radiation. The yellow line is the same thing, but with a correction factor to account for tides close in, so it goes up close in. You can see that the mass loss rate declines steeper than this energy limited scaling, especially as you move in kind of farther from the star. And I didn't see a significant difference when I turned on conduction to the base. As Ruth mentioned, that can be an energy sink. So for this flux range, it's not significant. So I'm going to move on to some of my current work, which is working on the smaller planets. They're sort of more interesting. Everyone's excited. So an Earth-sized planet, for example, would be able to have a greater metallicity in the atmosphere, leading to a greater mean molecular weight. The smaller planet size means that the outflow temperature is lower. Both of these things contribute to a smaller scale height, a less puffy atmosphere. This decreases the deposition radius, and so a smaller effective area absorbs the EUV, making it, and it also becomes harder for the wind to become unbound because it has to escape a deeper potential well. This is compared to, for example, a pure hydrogen and helium atmosphere. It also becomes really interesting because radiative cooling from molecules becomes important due to the lower temperatures in these planets where molecules could potentially survive throughout the outflow instead of being confined to a small layer at the base. So we can use our framework that we've developed for the hot Jupiters to analyze the outputs of the Earth simulations. So I run a preliminary model of a water atmosphere on a terrestrial-sized planet around a young sun, so higher flux. I'm assuming here that the atmosphere is hot enough that water vapor exists in the upper atmosphere that I'm modeling. So this would be a warm planet, not a hot one where the water would all be photodissociated, but also not a cold one where the water would all be trapped in the lower atmosphere. So I just wanted to highlight the important radiative coolants here. OH, OH+, H2O, H3O+, they're comparable to the H3+ kind of cooling functions here. However, unlike H3+, H2O is not optically thin, so that really needs to be modeled more in detail. For now, I just assumed optically thin emission. So starting from an arbitrary initial profile in blue for temperature and velocity, the atmosphere evolves to the orange profiles, where you can see the wind passing through the sonic point at about 3.5 kilometers a second. So the Earth will experience hydrodynamic escape with this EUV input flux. And here's the composition with altitude, where the neutrals are on the left and the ions are on the right. It's kind of a spaghetti plot. This is with a full water chemical network with all the reactions. So you end up with a mostly neutral hydrogen outflow by number, so that black line over there. Oxygen is present as well, so that's going to be the purple line for this relatively high flux from the star. So I attempted to run a simulation for a sub-Neptune with the same setup, and that did not produce an outflow. So at some point with increasing planet size, the outflow will be shut off for a primarily steam atmosphere. Later on, Eric might mention that water cooling in a hydrogen-dominated atmosphere decreases the escape rates, which may be why an outflow wasn't seen for 100% water. So I'm interested if we do detect an outflow, can we place an upper limit on the water content? Can we say it's a primary hydrogen atmosphere around a rocky core or a secondary atmosphere composed of water? Thank you.
So we got time for maybe one or two quick questions.
Yeah.
Michael, yeah.
Yeah, I'm really curious about the steam atmosphere. How many chemical reactions did you include? Like, how confident are you that you included all of the relevant ones?
I included 90. So this is the chemical network from Johnston from the water paper. You know, photodissociation, photoionization, all of the relevant. Yeah. I don't. Yeah, I don't know. I'd have to see. I mean, I think photoionization and photodissociation are the most important ones, and yeah.
Time for one more? Yeah.
I'm Skylar Larson from Cornell University. I'm an observer, I'm not a modeler, so I don't know too much about the whole modeling process. But would using this model for like more molecules, more processes, and especially for small events, is that like a lot more computationally intensive for doing like a hot Jupiter, or like how would you compare the two processes?
It is definitely more computationally expensive, but I run this model on a laptop in a few hours, so it's not
Doesn't matter.
super heavy to run.
Awesome, very cool. Let's thank Renata again. All right, great. Next, we have Alexandra Lehtmets to tell us about the atmospheric escape and chemical fingerprints in ultra-hot Jupiters.
Okay, hello from me too. I'm from University of Tartu Observatory, Estonia. And I will take you away from cooler stars and smaller planets to hotter stars and hotter planets, you can say. So this is mostly sort of preliminary work, kind of an idea phase. So there's not much results yet, but I can show you what is the idea right now. So basically, the motivation that, as we have seen from other talks, is that the atmospheric escape depends on also chemical composition, not only radiation and gravity, which is basically having kind of the main topic also here. And the observing escaping pieces reveal both physical and chemical processes that happen in the exoplanet atmospheres. And for that, I have this model that I have used is called beta ratio, which basically compares the stellar radiation pressure force compared to the stellar gravitational force. This model is basically meant mostly for we have a star and just gas around it, but it can also imply if you have the atmosphere escapes, and then what happens to the gas, or basically the evaporation tail. So we have here radiation. Radiation basically wants to push the tail away from the star, and then we have the gravitational thing that wants to pull the tail towards the star. And we were looking with this model into the atomic and ionized pieces, what could go towards the star and what not. And so we have here, for example, sodium and potassium neutral, which they basically want to go away from the star, following the yellow line. And then we have here hydrogen and nickel. There's also helium here, which basically want to go towards the star. And why this model was made, I will talk about later, but there is another idea behind it. And then the goals of this idea is to use the existing observed data from confirmed molecular detections of like ultra-hot Jupiters. Then we will study these ultra-hot Jupiters and specifically around early type stars, A and F type stars. And we made the criteria that the ultra-hot Jupiters have equilibrium temperature over 2000 Kelvin, and they are their distance from the star is 0.07 AU. And then we will investigate how the detected species trace the escapes. And if we have a constant escape, then we have also evidence of atmospheric replenishment. And then here is the idea that we are working on is the stellar contamination, which is not from exoplanetary spectra, but how the exoplanet atmosphere can contaminate the stellar spectra. And here we have a sample, and here are also some of the detections of these ultra-hot Jupiter atmosphere molecules and atoms. And I am working with the AER space mission homogeneous stellar parameters working group, where they have a sub-working group of looking into homogeneously derived exoplanet parameters. And for me, I'm deriving homogeneous planetary parameters for all of these planets using test light curves and from Area Stellar Characterization Working Group their stellar parameters. Yeah, and for the chemistry, this is just an illustrative plot how the bands of different atoms and ions usually can layer in typical ultra-hot Jupiter. Alkali metals are efficient traces of the upper atmosphere, like I mentioned, potassium and sodium, and metal oxides are in the more inner part of the atmosphere, and they are doing the thermal inversion in the temperature profile. So the idea that we have that the planet atmosphere can evaporate and accrete onto the star. There was also mentioned in the invited talk about the atmospheric escape torus. So this basically can also be a torus around it, or it can also accrete onto the star. And how that is possible is that these types of stars that we are looking at have radiative envelopes, so they don't mix the layers well, and the contamination can stay on the stellar photosphere long enough to be observationally detectable. And this idea was proposed by Chairman and Kama 2018, and Kama 2022 also did this analysis for KELT 9b. Unfortunately, they didn't find any evidence of it because actually the star, that KELT 9, is too hot for this to happen. And as previously shown, we have these if you have weak stellar winds, then we have this forward tail and backwards tail. And these early type stars have weak stellar winds. So to look into, is it actually possible for these ultra-hot Jupiters? We have this CAM-STAR model, which basically tells us about the photospheric contamination fraction. If this fraction is 1, then the stellar photosphere has been contaminated. And if it's 0, then no. So we have here in the color scale the contamination fraction. And here we have stellar parameters, mass and rotational velocity. And we can see there are actually, and here is the KELT 9 that the Kama 2022 has looked into, and they didn't find any evidence. And we also have assumptions of the planetary mass loss rate and the duration of the accumulation of the gas. And the lowest detection limit is 10 to the minus 6. This is derived from KELT 9 but it is better if it is lower. And this has been actually proven in protoplanetary disks. For example, my colleague has observationally found evidence of phosphorus contamination on the stellar photosphere. And they are looking now more into sulfur and oxygen. So here I made a plot of escape from propensity, which basically uses the beta ratio and tries to find what are the most likely species to escape from the planet atmospheres. And here is some of the ultra-hot Jupiters that is in my sample. And as suspected, alkalis dominate the radiative escape, and then we have calcium, and we also have vanadium, which is very interesting. And yeah, titanium is also here. And the threshold is also taken from the beta ratio, where beta ratio is 1. If it's lower, then it is very less likely to escape from the atmosphere, and if it's higher, then it is very likely. Yes. So the conclusions is that, as shown before here, that the chemical makeup strongly regulates atmospheric escape, and we already have existing confirmed detections of it. And we also have this initial idea of stellar photospheric contamination by the exoplanet atmospheres, which can also give us an indirect view into the chemistry of those planets. And future work is to extend it and also try to find atmospheric compositions of other planets that didn't still have it, and maybe do like observations of it, but that is still in discussion. And for the next slide, I want to show you the weather patterns of the exoplanet WASP 121b, which is very cool. Thank you.
Awesome, thank you. Topic close to my heart, so it's cool to see some ultra Jupiters. Any questions for Alexandra? Yeah, Erica.
Hi, Erica Egid from the Johns Hopkins Applied Physics Lab. The idea of using stellar contamination to probe atmospheric composition is really cool. This is the first time I'm learning about it. How much of the atmosphere would have to be lost to sufficiently distinguish between describing the stellar metallicity versus knowing that it is contamination from the exoplanet's atmosphere?
Yeah. The thing is, there is no detection for exoplanets, and that's why I'm looking into the ultra-hot Jupiters, because they have very high mass loss rates. And if you have compared them with my colleague who's doing the protoplanetary disk, they kind of have the similar mass loss rate, so it could be possible. And about what was the second part?
Just how sure can we be that we are measuring stellar contamination due to the planet's atmosphere versus just constraining the stellar metallicity alone?
There is an idea also connected to the beta ratio that I have shown here, that this can also describe actually the stellar atmospheres of how the atoms and ions go, do they want to go more to the surface or more to the core? And if we look into only the chemical species that have the beta ratio as 1 in those stars, that could be like our baseline for the stellar metallicity. And because for A and F type stars, solar metallicity is not very good charge, you can say, for the metallicity of that star. So we are also looking into that idea right now.
Cool, thanks.
Thank you.
Cynthia in the back.
Yeah, Cynthia Froning, Southwest Research Institute. As a follow-on question, do you expect the material that's been captured on the stellar surface to have a different velocity profile than the intrinsic lines from the stellar atmosphere that would allow you to determine that you're seeing accreted material?
Yeah. You can say that, because the most likeliest stars that we are looking for have very low velocities. And if you look into the, can I go back? We have this here, the rotational velocity, and we can see it's more likeliest if it has a lower velocity than higher for the star. And I don't know much about the stellar physics or the spectra, but it basically mixes more, the lines mix more into the very broadened lines of the stellar spectra if it has the more faster rotation. So that's why we're looking more into also lower velocity stars, but the thing is also lower velocity stars, they could be they can rotate so that we are looking here and they rotate this way. So we can't actually get the actual velocity or rotational velocity of the star. Thank you.
Time for one more, just in the back.
Where does it fall onto the star? Is it in the equator or is it
Can you repeat?
Where would the material fall onto the star? Would it fall onto the equator of the star, or would it funnel into the poles? Or
we are mostly expecting it to fall where the orbit of the planet is, circularly go towards the star and then fall. So there is also actually, you can see through the layers of when it is spiraling into the star, if you look into the stellar spectra. So we are looking more into transiting planets, and those in the sample are all transiting.
Awesome. Let's thank Alexandra again. Awesome, great. All right, our last talk before lunch, we got Eric Gaidos telling us about water-cooled planets getting better gas mileage.
Okay, can everybody hear me? Am I good? Excellent. So first of all, let me add my thanks to all the organizers for what I think is going to be a great workshop. I'm already enjoying myself. And then also the speakers before me this morning who have set the stage by motivating why the chemistry of the atmospheres are probably very important in understanding the evolution of those atmospheres through the mechanism of escape. And I would like to tell you a short story which takes us one step further, which says that basically what's happening in the interior of the atmosphere, deeper in the atmosphere, in the interior of the planet, is linked to that. And I will use as an example the most simple process, which is simply condensation of an important constituent in the atmosphere. And here, this is water. So this is work in collaboration with Tatsuya Yoshida. He did the heavy lifting for the modeling. So I want you to, of course, give credit where credit is due. And although he's at the Faculty of Science right now at Tohoku, he's moving to the Institute for Science in Tokyo. So if you're there for Cool Stars next year, please look him up. Oh, and also there is a nice QR code where you can read the paper which we published earlier this year. So this is motivated by now the ability to look at not just the evolution of planets at a single snapshot in time, which I think we've been sort of used to, but actually look at them in time using our ability now to estimate the ages of stars, of the host stars, with the assumption that the age of the planet is very close to the host star. So if you do this, for example, around M dwarfs, and the Kepler M dwarf sample is one of the best characterized, although not necessarily the most accessible now, we see in the radius distribution this classic dichotomy between the rocky super-Earths and the sub-Neptunes, which we think have these hydrogen-helium-rich atmospheres. And if you then categorize or group these into the younger half and the older half, you can actually see the evolution versus time. So you see that the sub-Neptunes are initially highly populous, and they disappear over time, and they turn presumably into the super-Earths, which are rising in number. And so this led to another observation which motivated the study that Tatsuya and I did, which was to look at this evolution now with distance from the star, here expressed as irradiance in Earth units, and again, dividing the sample into hotter and or older and younger planets. And you see that actually there is a suggestion here that there is an intermediate distance at which sub-Neptunes are less likely to disappear compared to their counterparts closer to the star, which are highly irradiated, and further from the star, which I will suggest might be due to ineffective cooling, which at least to the distance that we observe might be overriding the effect of the 1/r² of the irradiant X-ray. So as Ruth said, the important consideration here is this balance between the irradiation coming into for XUV-driven escape, the radiation coming in from the host star, and the ability for the upper atmosphere to radiate that away. Otherwise, the energy has to go somewhere, and usually that's in the escape of the atmosphere, if not by conduction. So what we did was take basically adopt a complete self-consistent hydrodynamic flow, which includes radiative transfer, which is wavelength dependent through the atmosphere, also coupled to a self-consistent kinetic model. There's no LTE here, it's all purely kinetic, to calculate the effects of adding different amounts of water to the base of an atmosphere and the effect of that on the escape. So we do this, of course, versus time because we have to study the evolution, and so we basically model that of a typical of a typical M dwarf, and we look at essentially the escape rate over time driven by the XUV radiation as a function of the upper atmosphere abundance. So this is the base of the model simulations above which everything important basically happens for this XUV-driven outflow. And that's about 100 nanobars or so. So you see basically here this effect that basically if you increase the water abundance up to about 10%, you can decrease, especially early on, the rates of escape of the atmosphere by an order of magnitude. Later, these converge. So the effect of this on, of course, the atmospheric mass is that those atmospheres that are water poor tend to disappear more rapidly, and that the radius of the planet basically decreases, no surprise there, more rapidly over time. So while water-rich sub-Neptunes can persist for many, many gigayears, those that are water poor can disappear in less than a gigayear. So what controls that upper atmosphere water abundance? Well, partly it's due to the fact that the planet itself will have some abundance of water, but water, of course, is condensable. And sufficiently far from the star, water will tend to rain out. It may not form an ocean, but it will condense into clouds and basically be inhibited by something we call the Clausius-Clapeyron relation from being abundant in the upper atmosphere where it actually matters. So this plot basically shows the lifetime of atmospheres, basically as a function of the irradiance from the star, so further from the star to the right, versus that water abundance now, which ranges from up to 10% down to basically 0. And these are the lifetimes here. So basically water-poor atmospheres that are very close to the star will disappear very quickly, and those that are further from the star and have large amounts of water in the upper atmosphere can live basically forever. But what's going to dictate this is basically the fact that water, as you move to lower equilibrium temperatures, will decrease. And that's that dashed red line here in a simple model of how that relates to a radiative convective boundary temperature as a function of distance from the star. And where you see basically the dashed red line here intercepting the 10 gigayear profile, we would expect long-lived sub-Neptunes. Well, those that is falling below, we would expect to disappear. And of course, up here, there's some upper limit, of course, to how much water you can expect in an atmosphere. These are very high metallicities. And so again, you would expect the lifetime to decrease. And this intermediate range is this kind of sub-Neptune oasis, which might explain at least the preliminary statistics that we see from Kepler. So you can look at this again now, the same sort of picture now with radius, and basically here is the oasis, and these are different ages as well as different emissal mass fractions of the atmosphere versus time. Of course, if you start out with more atmosphere mass, it takes longer to erode. But again, you see basically this intermediate zone, which is at and slightly more than the solar constant for the Earth. So this is the habitable zone here, where sub-Neptunes can persist for longer periods of time. And then interior to this, XUV overrides any cooling from the water molecules. And by the way, I should add, as the previous two speakers ago said, it's often the dissociation products of water that are important, like OH. So water is not very good under UV radiation and wants to photolize. And so OH is an abundant product, but also OH is a little bit lighter, and so it can go higher in the atmosphere. And then further out from the star, of course, you get the cooling, but eventually the fact that you're so far away that the XUV drops off, you should see, and we predict, we should see another rise of older sub-Neptunes that have survived to the present epoch. So I've used 10% as an upper limit. We don't really know, of course, how much water is in these atmospheres. And of course, it might vary strongly. For example, what if there is just no water in the atmosphere? Why would that be? Well, JWST, in a completely different workshop, we might be talking about this result. JWST has shown that there is this curious correlation between the mass of the star and the abundance of water in the protoplanetary disk. With very low mass stars, that is, say, less than 0.2 of a stellar mass, having disks that are very water poor, essentially no water in them, you get hydrocarbons instead. It's a very high C to O ratio. Whereas those around T-Tauri stars of a solar mass like the sun tend to be more water rich. There's, of course, variability. So what happens if you form planets around these stars? Well, the expectation is that basically you flatline the sub-Neptunes because there is no longer the oasis that never started out water-rich to begin with. And so you have rapid disappearance by 4 gigayears of planets all the way out to basically beyond the habitable zone, where XUV, again, sort of drops off enough that the sub-Neptune atmospheres can preserve. So you would predict around the very low mass stars that you would see a deficit of sub-Neptunes relative to, say, higher mass stars. And so these very low mass stars are the late M dwarfs. Everything more massive is basically early M dwarfs and larger. And in work out of the CFA by Ment and Charbonneau, actually finds this effect for at least the sample of objects that we can now probe. So the ratio of rocky Earths to sub-Neptunes around slightly higher mass M dwarfs is about 1.6 to 1. Well, that around very low mass M dwarfs is 14 to 1. That is, there's a complete deficit of sub-Neptunes. There may be other things that, of course, influence the statistic, but this water poor initial condition might be one of them. And so we can basically do this. We basically generated these plots of basically in our modeling to generate these results, the escape rates versus the important things that matter. That is basically the X-irradiance and the gravitational acceleration, which is basically the depth of the potential well, as well as the water abundance itself. Represented here is this little constant R. And so in the paper, I would encourage you to look these up. These are basically available, again, to do your own sort of simulations of what your particular favorite sub-Neptune might experience as it evolves in time. And you can do this sort of parameter analysis now, where the results that I showed was for a particular core mass. We expect this to vary. So this is now looking at irradiance and a distance from the star versus core mass, and calculating what mass fraction in the envelope you has to have in order for the envelope, some of the envelope, to survive to when we would typically observe it, say 5 gigayears. And so here is the oasis here. And so up here, very small amounts of envelopes will survive. Down here, essentially no plausible envelope mass fraction would survive to the present day. So the oasis is here. You can see it's more subtle here now, and only present for a certain range of core masses. We would expect that. But this is the kind of thing that we can do now in order to make predictions for the populations that we would see when we start to more precisely age date the host stars of planets that we are finding in say, TESS and in the future Plateau. So to sum up, so from the Kepler statistics at least, we see some evidence that temperate sub-Neptunes appear to lose their envelopes faster than their warmer counterparts, maybe not as fast as the very hot counterparts. And our hydrodynamic outflow model, which includes self-consistent radiative transfer as well as the kinetics, with Michael's question about 70 reaction rates. And remember, this is only for hydrogen, helium, and oxygen. This could be due to a dry upper atmosphere for the temperate sub-Neptunes, and that the absence of sub-Neptunes around very low mass stars could be the result of an initial condition, which is basically water dry. So in the future, as an observer, I want better statistics. So TESS is giving us now with long period planets being discovered, particularly around K dwarfs and M dwarfs. We want to improve our model. I mentioned that only hydrogen, helium, and oxygen include. That's a lot, plus electrons. So carbon is the thing that we want to add next. So Tetsuya is working on this. And of course, we want to investigate whether there are some interesting populations level statistics now that we can do by combining the JWST observations of disks along with planet population synthesis models. And then finally, we should be able to see this, right? We should be able to make a prediction that as we march out in semi-major axis, the water abundance in these sub-Neptunes should drop off over time this is a very clear prediction. JWST is a water finder. And this is the water at 1/10 of a microbar, which is right where JWST is suitable for finding with transmission spectroscopy. Thank you very much, and I'll take any questions.
Thank you, Eric. We got time for one quick question. Mike.
Mike Jack from University of Colorado. Have you thought about the implications of these results for Venus? How long would it take to lose an initial ocean of water from the Venus atmosphere to space?
We are working on that problem, and we're not quite ready to present it at this conference, but stay tuned. Yes, exactly. So this has implications for whether or not Venus ever actually had a water ocean.
Thanks.
That's very intuitive.
Very cool. All right, thank you, Eric. All right, we've got just a couple announcements for lunch. Lunch will be in the cafe where you had breakfast. There are Slack channels for each session. So if you have like follow-up questions, feel free to go to those, join those, and you can ask anything there. Any other questions or announcements? Yeah, and then speakers should go follow up and look in those session channels, see if there's any questions for you there. Otherwise, have a good lunch. We'll meet back here at 1:15.